is Jorginho. Today I would like to present lab 5. For our lab, we actually have 5 modules. First is our basic clock. It has show the LCD display. It has a analog clock, digital clock, LED, and alarm on off. Besides, the RTC control 1 second timing by the time second interrupt. Okay, next for the second part is alarm clock. The RTC will keep track of time, and sound module play select music based on time. This is alarm clock. Alright. Next, we talk about the music module, where next it is sound module. Sorry, for the FDM1, is used for the PWM to control the note, and then the FDM0 is time overflow and is control the tempo. For the fourth part is music module. There's 3 songs to be played. First one is when the stand go machine in. Second one is Twinkle Twinkle Little Star. Third one is our custom song. For the special case, the custom song is using C6 to visit and stop when G is 0 to correct custom song for alarm. See, let's see about the custom song. This
so no song found.
And it's something like this. For C6 to be 6, and when it is 0, it will stop. Alright. Hello, I would like to talk about how to explain the IDC setup. Firstly, we go to the initialization RTC here. Here is the initialization of RTC. First, we enable the clock with SIM ACGC6, and we unlock 3 register, which is LR lock register, SR starter register, and CR is control register. Next, for the SR, we stop the time by switch off the time counter. Then we make the stabilize, make the 332 and 768 kHz clock to stabilize. We need to enable the oscillator for the CR, and then we disable unnecessary register, which is TPR, prescale register, TSR, time immediate flag and overflow flag, and TAR, alarm register. Then we can start our time counter by using SR setup register, and we set the IER to enable 1 second interrupt, and this is waiting for the interrupt to enable. Next, for the RTC second interrupt handler is linked to the digital clock. It will explain later.
Hi everyone, I'm Kok, and now I will continue with the presentation just now. So right now we will be now dealing with the digital clock. So in digital clock, the most important thing is the seconds will increase. So since this is using RTC 1 second interrupt, so the second will increase every seconds in real life. So we will do some algorithm calculation here. If seconds is 60, we will make the seconds reset back to 0 and plus 1 minute. Same things goes to the minutes. If 60 minutes has passed, 1 hour will increase. And lastly, if 1 hour has passed, 1 days will increase. So these 3 seconds, minutes, hours, of course, as well as days, months and years are actually global variable. So we only need to declare it since the beginning in the main, where we don't need to pass it around to use it. So next, this is to calculate for every single day. How about what happened afterwards? We will go into the current date. So 1 year we have 12 months. For January, March, May, July, August, October and December, we have 21 days. So what happened is, if the days has passed 31, not 21, 31. So if the days has passed 31, we will reset the dates to 1 and increase the month. So of course, if 1 year have passed, which is the month has become 13, it will reset the month to be 1 and increase the years by 1. What happened is, this will only occur when month is December. So apart from these months that I mentioned just now, we have some special case, which is the February. Since you should know, February in normal year will have 28 days, while in leap year, which happen every 4 years, will have 29 days instead. So doing the algorithm years modulus by 4, we will check whether is it repeating 4 years. For example, 2000 is a leap year and 2004 will be a leap year. Right now 2017 will be a normal year, and 1 year ago 2016 is actually a leap year. So same things for the calculation. Days, if greater than 29, then it will reset and plus 1 month. Otherwise, if it is the normal year, then if it is more than 28, which is the 29th days, it will reset back to 1 and month will be plus 1. For all other months such as April, June, September and November, it will be always be 30 days. So same things goes. So the important thing, apart from the months calculation, we also have a day of the week calculation. So this is the index that we use to perform to show what day are we right now, Monday, Tuesday, Wednesday or anything. So the algorithm is here inside this. This algorithm, we get it through online, is proven and ready-made algorithm by some expert previously, where the calculation is based on the patterns, and with this algorithm we will correctly pass if the days, since we pass the year, month and days into it, it actually knows which day are we in, and then it can return us with the correct index, and that will be shown in our clock interface. So take a look at this first. Since mentioned earlier, we have an analog clock, a digital clock and a date. So today is 25th, it's a Saturday, which is correct. So you can see that the time for the second for the analog and the digital is is increasing for every second, sorry. And then later you can check that if it is greater than 1 minute, or if after, let's say right now is 59, we can wait and you will see that right now is 12 a.m. and later you will see to be 1 a.m. in, let's say, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1 a.m. So you can see that the hours has been moved to 1, the minutes hand is staying at the 12, and the second is still continuing. So this, it can show that the seconds will increase after 59, will add 1 to the minutes, and 1 minute will add to the hours. So here is some algorithm that you can see from the coding wise. First of all, we draw a circle for the analog clock. This is to delete the previous hour clocks, the previous hours, minutes, and seconds hands. So here we put this to indicate whether it's a 12 o'clock, 3, 6, or 9. And finally, this is the more important concept of making the hour hand. So assuming that we will have 12 o'clock and we are getting a 1 o'clock instead. So the straight one is something that we don't want, and then we want to print a hour bar, let's say, at this position. So in the LCD screen, we have a function called draw line with initial position x0, y0 and x1, y1 at the final position. To draw this line, we have one angle from the center. So what happened is, to get this x1 is actually a location away from x0. So this x is simply sine theta. Same thing go to y, so I will explain the sine theta first. In this case, theta, we know that in the Code Warrior C programming, we don't have a degree, so our theta have to be in terms of radian, which any theta, any fraction should times a 2 pi. 2 pi is a circle. So doing the calculation that we have 360 degrees in total. To get this fraction, knowing that if this is an hour hand, there are 12 hours in one circle. So dividing 360 by 12 is actually 30. So 30 over 360, this is a fraction, and we will times this fraction with the 2 pi. And this will give us the theta instead. So by putting this into sine theta into sine, so we will have an x. Of course, x0 plus with this, we will have the final position. But thinking of that, sine theta is not all, because we have this hypotenuse. So making use of this, we are actually having some constant variable here. In this case, we use 30 to make it, in this case, we use hours. We use hours constant, which is 15, sorry, not 30, which is 15, you can see from here. So thanks to this, we are able to create a correct with origin x, origin x plus hours sine 30 is here, 360 is here. It's always a good practice in Code Warrior C programming that you multiply everything, then only you divide, because after divide sometimes you will lose some data. And you can see hours minus 1 here and hours here. This is to show that whether current hour is 0, 1 or so on. The example just now is because I want to get the time at 1 o'clock. So what if I want to get a time at 4 o'clock? So 4 times 30 divided by 360, you will get a fraction as well, and times the 2 pi. And end up, you will get the analog location of the hours. Same things go to minutes and seconds. Besides, the only difference is, for example, just now we have 12 hours in one circle, and we should have 60 minutes and 60 seconds in one circle. So dividing 360 by 60, you will get 6 instead of 30. And same thing goes to minutes and seconds, is a global constant. And this concludes what happens in the analog clock, which is a challenge for us as well. So finally, we will have a short display of how does the date, time, alarm to be shown. So this date is having the, see, this is the one that we use, the day of week index we get from the previous function. And today is, as you can see, is Sunday, Monday, Tuesday, Wednesday, Thursday, Friday and Saturday. You can see from here. So with this array, we will know that which index it is to save as a first value. The other 4 will be the 2 digits and 4 digits, which are days, months and years respectively. We will save this in a variable, temporary variable called date, and we will print the date, because LCD put str, this have to be a character array, and we right now save all this information into a string, which is a character array. So same thing goes to the time, hours, minutes and seconds, as well as alarm. We just show the alarm here with the hours and the minutes only. We can set the seconds, and I will show it later. Finally, just to show the users that whether the alarm is on or off, we have an on-off display in the GUI just now. And this is one of the extra function that we do, because it never state, the lab sheet didn't state that we need to do that, so we think it's more convenient to do so. And that complete the whole clock interface and how the clock can go off for each minutes, seconds and hours. Thank you.
Now I would like to show you how to set the time, and that first we press the center switch, we go in, and let's show about the date first. Change that menu, and then first for the December, yeah, 21, right? Then we go for November. We don't have 31, it will become 11, and it will be 30 only. We don't have 31, it's correct. And then we try again for 20, we have 31. From 9, from 9 is 30. Okay. For the special case, this February. This is not a leap year, and it is 28. It's correct. Let's try a leap year. 2016. It's correct. Alright, let's show you about the to change the time. Time is 0. 59. It's 11, right? 23. 59. 40. And replace the center. Alright. And back to red. Let's see. Start from 40, 47, 48, 49. And the date is correct.
4, 3, 2,
1. Yeah. Because we didn't select the alarm music. So alright. Let's go for 1 January and 2018. Okay, thank you.
Okay, now I will explain about how does the alarm clock works. First, let us look at the coding. So the alarm clock is mainly using the RTC to trace the time and use the FTM to generate the music. So if goes just into the alarm, this is the continuous loop that we will be doing, the clock system. So if the alarm is set and if the hours is this hours is the one that controlled by the RTC just now, and the hours is, minutes is, and seconds is, this is the alarm that has been set. So if this is done, then we will set the alarm trigger to be 1, and if the alarm trigger is 1, we will have different cases of music will be played. Depends on the alarm tune. So if nothing happened, then we will display the time as usual, which is the analog clock and so on. So right now, we will go into the watch and see how does the alarm clock has been controlled. So we have set alarm and set alarm tune. Let's go to set alarm. So in set alarm, we will have a change alarm and some algorithms to check which alarm it is and display it correctly, as well as choosing the correct alarm here. So this is some special functions that we created, which will help us to reduce the redundancy of the code. If you get the switch, then you will change the time and by given a maximum. So this to differentiate between hours and minutes, and as well as seconds. So same things to go with specific submenus, and this will be explained later as well in the additional features. So the important thing right now is, let's see the user interface. So to set the alarm, we press the center, then you can go into change alarm. So with this, currently the alarm is 12 o'clock and 00 seconds, which that's why just now it will ring the alarm, because the alarm is set if you look at the video again. So right now, let's say if I want to choose 1 o'clock, and let's say I want to choose 58, maybe some seconds, maybe 10. So this is where we will control the on and off. If you go up and down, it doesn't work. Only left and right work. And you have to press the center whether you want to on or off. Right now, we just off it first. So this is to set the alarm. You can go back and manually check. This is off. 1 o'clock, 58 minutes. Right now it's 12 in the system, so we will change the time to 1 o'clock, maybe 58 instead. We put 50 for example. Okay, So right now I will show you about the alarm tune that we have. We have 3 songs: When the Saint Go Marching In, Twinkle Twinkle Little Star, and Custom Song. So I will show you about When Saint Go Marching In first. You can press the center to set it. So right now the Saint Go Marching In has been set, and the alarm is on. So with that, we can actually reduce this to make it happen faster. (51 minutes), okay, with the time of 57, so 51, let's go to 56 and go back to main. So, sorry, just to check, this is 10 seconds. Okay, 57, 10 seconds. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is slow because of the tempo. We set it to be 1 second. Every notes will be played with 1 second. So this is the bass that I actually add. So later I will show you how do we change it to make it fast. So as mentioned, we need to stop it whenever I want, like this. So we can stop it whenever we want. So this is the showing of how alarm clock works, and right now I will show you about the FTM, how does the music is generated. So the FTM, we will have, hold on for a second. So for the FTM, we actually use two port of FTM, 0s and 1. And now let me explain how does FTM work. First, we initialize to enable the clock for FTM 0 and 1. FTM 1, channel 1 is the one that we use to control the notes, where FTM 0, without specifying which port to use, we use to control the tempo by using time overflow. So as for FTM 1, channel 1, it will be PTA 13. So we use that using the PWM instead of output compare to make it sort of different. We set on another hand, for FTM 0, we set the mod, which is the maximum value, to be 0x FFF, which is 65535 for easier calculation. Right now, all we do in the initialization is setting the FTM1 channel 1, and we start the PWM. So PWM pulse width modulator, we use FTM1 channel 1, SC, MSB, and LSB. This is to set, for the LSB is to set for the rising edge, and you can check it through the datasheet. So we use only the FTM 0 interrupt, and that's why we didn't use, and that's why this is to show you. So since FTM 0, we are using the time overflow. When we enable FTM 0 interrupt, we will use a TOIE for time overflow interrupt enabled, and then we will start the enable IRQ for FTM 0. So what happens if it actually goes into the handling, which is here, FTM handler? So what happened important here is it will clear the overflow and reduce the tempo by 1. So tempo is a global variable. If you can see here, tempo is actually a global variable. So this tempo will start minus minus depending on what was the previous tempo. And we are dealing right now we are dealing with musics. So this is the play note that is important for us. In play note, we will pass a frequency, which is the notes, and the beat, which how much we want it to continue and lasting. So we will assign the frequency to the note for global use. For example, the FTM1 channel 1. We will control the notes here. If note is 0, so which means that it will be the stop. So it will play nothing actually, nothing. And in this case, we will have a tempo using the beat come in with times the 46. 46 is we based on this calculation here. So system frequency is 48 megahertz. We choose to use a prescaler of 4, which will divide the system frequency by 16. So it left with 3 megahertz. So considering 3 megahertz, 1 ticks is actually 3.33 times 10 to the negative 7 seconds. So we consider right now using an overflow. So the maximum of overflow we set is 0x FFFF, which is 65535. There are 65535 number of ticks in one overflow. So calculating the number of ticks times with the system 1 tick seconds, we end up in 0.022 seconds for each overflow. So this actually depends on how much time do we want. So this is the time. So to calculate how much do we want, we actually goes towards how long do we want for 1 bit as a tempo. So we considering initially using 1 seconds. So to get to 1 seconds, we need approximate 46 bits, which is shown here, 46. But if let's say the timing for 1 second is not really that good, we can choose to check, for example, 35, which will make it faster. So this is how we control the tempo. Besides, for the notes itself, since notes we are setting it as half period, so the PWM will have a mod and a CIV. So CMV is the half, is a time for it to trigger the toggle. So in this case, FTM1 we set it to the node, which is half period, and MOD is the full period, which node times 2. If you need explanation, it will be here. In PWM, we are using a rising edge. This is the mode, and this is the CNTIN, counter initialize, which is 0. So 0 to mode is 0xFFFF. This is the normal mode that we want, but because right now what happened is, let's say this is CNV, the PWM will be triggered at this position, and so on. So if your CNV is here, then it will last until here, then only it will start triggered. What happened is we set the CIV to be half period, which is the nodes. So full period for until the mod, instead of 0 FFF, we are right now using 2 times nodes, which is half plus half. So this would be 2 times nodes, and this is half, this is half. So this is how PWM works. And come back at this, we set the FTM1 to be 1 to make the PWM clock works. And if this is 0, we will set the clock to 0. Prescaler of 7 that is used for the nodes. So we will divide it by 128. The prescaler 4 that I mentioned just now is here for the tempo. So this is for the tempo prescaler 4. We will make sure that it runs always, so even though the nodes is 0, it will still running. And this is while the tempo is greater or equal 0. This is to do nothing. What happened is, since the tempo is controlled by the global variable tempo and the FTM0 interrupt handler, so it will, when it reaches 0, because just now is tempo minus minus, when it reaches 0, then only it will goes out of this while loop. So after out of this while loop, we will set the FTM1 to 0, which stop the clock for the nodes, and we set the buzzer to off. So on buzzer has another function previously. And lastly, yeah, we will stop the FTM clock for safety purpose. And this is the buzzer initialize. So initializing the buzzer, we have enabling the enabling the clock. We enable the buzzer PCR, which is a global variable, actually is a global constant, to max 3 because it's a PTA 13 is in altered 3, DSC for the high drive strength, and PDDR is the output of the buzzer mask. So you can see the global variable here actually. Buzzer mask is 13, PDC is A and 13, PDDR A, PCOR A. So this is to stop the buzzer from beeping. And here is finish the, so here it will be finishing the coding explanation, and we will now take a look at how do we actually stop the alarm. So the alarm is set at 12 o'clock. So I will simply change the time to 12 o'clock instead. Maybe 11:59, 41 seconds is good enough. Back to main. So we will wait. Let me set the alarm tune first to this. Okay. 54, 55, 56, 7, 8, 9 rings. So this is slow, so we can simply interrupt the alarm like this. So we can cancel it whenever we want, and right now I will show you on the coding that we changed just now, which is here. I changed it to 35 instead of 46, and let's give it a run. Hold on for a moment. Okay. So take a look at here. To make things easier, we actually can check the alarm straight away by pressing the right button here. So this is faster than just now, and if you want to be faster, you can go back to just now that function to change the beat tempo. And now this is all from the music generation, and thank you. Now is the interesting part in our design this time. So everyone is given an opportunity to do something extra in our device. So here is some list that we actually done. PWM, we use PWM instead of output compare, because we know that most of the students are actually using output compare, and we personally realize that PWM is easier to use than output compare in our system. The next one will be the custom song that we implement, which will be demonstrated later. The lyrics is considered as a challenge, so the requirement was to put the music in Twinkle Twinkle Little Star, the lyrics following the tunes, while for music one, which is when saints go marching in, it doesn't require, but we still add to make ourselves a challenge. And the alarm on off previously was not mentioned in lab sheet, but it is mentioned in the vlog criteria, so we don't actually treat this as a new extra thing that we done after this. And what happened is, let me show you the custom song. So everyone is using the preset songs like When Saints Go Marching In and the Twinkle Twinkle Little Star. So our inspiration is the Nokia and Sony Ericsson phone previously, where you have a keyboard. So this keyboard will have the sound of Do, Re, Mi, Fa, So, La, Ti. This is C6 to B6, and finally we have a 0, which is a gap in between. So you can actually add on with some others. For example, more of this, and more of this. But okay, what happened is, if let's say I don't want this, I can push up to delete. So let's say I can add in more right now. Oh, sorry. Yep, that's how it works. So for example this, and then we will test it out by pushing the to right. Each of them we can check straight away from here instead of waiting for the alarm, and this is how it goes. Okay, and let's say I choose this as a custom song, and let's say I set an alarm. Yes, go back to main. No, this is not the time. We change the time. Let's say 0, maybe 59, 23, and yep, 10 seconds to go. 9, 8, 7, 6, 5, 4, 3, 2, 1, go. So stop it. Yeah. So this is one of the most thing that we done that we are proud of. And in terms of coding, we do implement some C programming understanding. For example, the custom song that we do, we are using the dynamic array, which can be found here. So dynamically array can resize throughout the program. So we must first initialize using the malloc. This is in C programming. This is the extra thing that we do, and we can change the size in the function here. Where was it? Yep, here. Reallot. This is reallocation. So this we will change the sign. We will change the size dynamically every time it adds and every time it reduces. And to make it basically, to make it simpler, we actually have the following functions: set specific time and set specific submenu. So every submenu, everything that we do, left, right, up, down, for changing, let's say between an hour or a minute, we use a submenu instead. So using a star asterisk, this is a pointer. So anything that pass into it after changing, for example, let's say I can case 1, choose between get up and get down. I have case 2, which is left and right. So this can be used in places such as here. I say it's set 1, which is up and down. Submenu is an address so to cope with the pointer, it will pass the variable by reference, so anything changes in the function will be passed out here without anything extra to be done. So 3 is the maximum value that I need, which is between 1, 2 and 3. So up down is to control the submenu here. Left, right will be the one to control whether you go to other loops or not. So for example of here is left, right instead, because down and up is to use to control whether it is an undo or it is loaded in with the custom key. So, and to show you another is specific time. So this is under the set alarm. So we have a specific time. We can use something like this to check whether up and down. The maximum for hours is 23, which is at 24 it will goes back to 0, sorry, and 59 same things to goes with minutes and seconds. So with this we simplify the code a lot and it helps in the efficiency. So the last thing that I would like to stress out is that I use the dynamically array of colors. So since we understand that all the constant background color, character color or select color is actually an integer, so we can have an integer of array of integer. We set everything to background color first, and then we will be here color submenu -1 equals select, because we realize that each of the submenu is distinct at its own position. So we utilize that information and turns it to select color. So with that, we dynamically change all the background colors and select colors depends on where you are. Like for example, this alarm, we never goes into this position, so it's always been background color which is the black color instead. And for select color is blue color. So that's all from us. Thank you. Now we will demo of the songs that we have in this program. When the Saints Go Marching In, Twinkle Twinkle Little Star, and custom song. First with When the Saint Goes Marching In. Now, Twinkle Twinkle Little Star. So for custom song, we can simply set a song, for example, now play it. Okay, thank you.
Hi, now I would like to talk about the 4 question. First question is what is the first question is what is the controller doing most of the time? I think this is the alarm clock is do the most, and for in this function is when the menu is equal to 1. It's like we press the center switch and it will go to the clock menu, right? So let's stop and we press is equal to 1. Then we go to the menu with the same logic here, and when the alarm is set to 1, it will, if the alarm is hit, that the hour is hit, the minute and second is hit, then the alarm will trigger. When the alarm trigger, it will pick the music that are select. Like for example, we select when the alarm is trigger. When the alarm is trigger, then you might choose from these 3. Next is the display time when the menu is 0 and the alarm trigger is 0. That means there's no alarm trigger and no menu is pressed. Let's go to main function. Okay, next question is what is the system frequency of your system and how do you set it? Okay, system frequency is equal to 48 megahertz. It's get from the clock.hash. What? Clock.hash library. Okay, sorry, it is clock.c. Yeah. It's step from here and initialize using initializer clock. Okay. For the third question is how does the system frequency affect your FTM module? For FTM module, it is depend on system frequency, divide system frequency by a prescaler. Get the required number of the tick for knot and tempo. Each tick has different timing depend on system frequency. Next question will be how does the system frequency affect RTC module? No, actually I think it's not actually directly influence on RTC. but necessary to synchronize using oscillator enable from RTC to stabilize 32.765 kHz clock. Okay, that's all for the 1, 2, 3, 4 question.